are similar to the Alexander Conway polynomial. So let us return and repeat something. For example, exercises of sheet 9 were not properly done. So let us look at first for the following thing. Also, we'll speak about braids today. So actually, the last sheet of exercises, number 10, was about braids. So we repeat about braids. There is a problem today. Raphael is ill, so I'm very anxious about what has happened. Maybe he's seriously ill. So it's then we shall look at solutions that I prepared, and I send you the solutions of for the braid group. So let us look the braid group. The braid group with 3 strands. This is the most simple, the simplest one, because with the 2 strands it's Z, so it's number theory. So we have the following relations for braid group. 3 strands, so 2 generators, 1 relation. And the exercise was about this element sigma 1, sigma 2, sigma 3, which we described geometrically as a twist, full twist. So if we just consider sigma 1, sigma 2, it will be half twist, and squared, it will be the full twist. So we consider you made exercise that this element is central. Actually, it is the generator of the center, but we don't need it. So this element is central. Probably we can say this is center of the, so I mean that this is the generator of the center. Sigma 1, sigma 2, sigma 1 squared is the generator of the center of the braid group 3, B3. So if we now consider the quotient group, this is the generated by same sigma 1, sigma 2, but you should add one more relation. This is that the central element goes to 1. Okay, so then it was proved that this becomes the free product, now without any amalgamation, so just a free product of 2 finite group, the simplest finite group of order 2 and order 3. This is a very well-known group. And we considered the homomorphism from this thing to PSL 2Z, so the group of matrices SL2Z, the matrices with determinant equal to 1, and for P we need to factorize by the center. It is not difficult to prove that the elements, the unit element and the minus unit element, they generate the center of the matrix group, and the quotient is called modular, special modular group or projective modular group. So this is this group, and H we consider as the quotient of our braid group by the center. So if we make quotient from one side, the quotient of the special linear group by its center, on the other hand the braid group quotient by its center, then these two objects they become isomorphic, and actually more or less the same. So how to prove it, because the proof that we considered last lecture was not sufficiently good. So let us consider what does the element of this group may be. So there are generators, sigma 1 and sigma 2, and so we take the product like this. We call this generator S. We take the product of this. It is the half twist, so it's more or less square root of the central element. And the group H is a free product of element of the group order 3 generated by S. So this element becomes element of order 3. This element, of course, is the element of order 2, because by its square we determine the quotient group. So what does it mean that it is what does it mean that this is a free product? We are doing, sorry, I make it more visible. Is it visible?
Okay.
Really? I can make, okay. So what do we need? As it is a free product, in this free product we can write element in one of the following form. It starts with S. Epsilon 1 may be epsilon 1, epsilon 2, epsilon r may be plus or minus 1, because S is the generator of the order group of order 3, so it may be, there are 3 elements, neutral, S, and S minus 1, if you want, or S squared. Anything is just fine. And T is only one, is the only possible degree is 1 or 0. 0, this is neutral element, so no problem. Then if it starts with S and ends with S, one possibility. Another possibility, it starts with S and ends with T, also possible. The third one, again, start with T, ends with S. Start with T, ends with T, and simply T. Okay, so all these possibilities represent, and you need to consider all of them represent an element of the free product. So let us consider our proof. We shall prove that this is injective. So that how to prove that this is injective? We start to consider elements. T. What do we define T as sigma 1, sigma 2, sigma 1. So we just make multiplication by matrices. If you remember, there is S goes to A, sigma 2, sorry, sigma 1, not S1. Sigma 1 goes to A, sigma 2 goes to D. So if you make a multiplication of matrices, you have this beautiful matrix with determinant 1. So T, for T, it's okay. It is not in the kernel. Then let us look at TWT. As T is of order 2, then we can write it this way, because T minus 1 is equal to T. So this element is the element conjugate to W. And the same way, T of W is conjugate to WT, the same way. So it is what it is necessary to check, that F bar of W, F bar WT is not 1. So if we prove this, then because it is conjugate, then it's also non-trivial, because if the image is trivial, then T minus 1 also trivial. Okay, the standard conjugation for the group theory. Okay, so let's begin this a little bit boring procedure. What do we have? WT starts with S and ends with T. So now we are using the braid relations, and we see that S minus 1T, if you look at that, this is T and this is S, then this one and multiplied by T is exactly this one. And ST is the image of this one, because by the definition, and S, this is 1, so S minus 1T is the same as S1. So we have this equalities. And where we denoted A bar, B bar, the images of matrices A and B in the projective special SL to Z. Okay. Then what we have? We have by definition WT is non-empty product of the matrices A and D minus 1. So let us look what we can easily look at these matrices A and D minus 1. They are beautiful, and they are all positive. All, I mean, that the elements of this matrix is positive. So when we can now consider the product, of course, it will never be negative, but even more, we can look what will happening after making multiplication of these matrices with natural numbers. So if you make a product either A by A or A by D minus 1 or D minus 1 A, anyway, you see that the diagonal sum at each time when you are making this product, the sum of diagonal elements augments. So will never such a product will be maybe equal to plus or minus e plus or minus e2. For example, let us I make a small calculation. So a multiplied by d minus 1. What is it? What it is? Like this, it will be, no, here you'll have 2, right? Here you will have 1. Here you will have 1. And here you will have 1. So at this product, here we have elements in the diagonal equal to 1. Here we have elements, sum of elements and equal to 2. By induction, we can see that it is strictly how to say, augmentation, growing, strictly growing function. So if never can be this one. So now what do we have? We proved by this, we proved for this F bar WT, and this is okay. Now what we can see is, suppose that F bar W is 1. We write this as it 1, then it equal to our F bar T, our beautiful matrices, but this is also impossible by the previous argument, because A and D minus 1 has only non-negative, matrix, and here the F of T is matrices of both signs, which is impossible. So because if you have this product, you have all will be negative, positive. If you would like to consider E plus 1 or E minus 1, you should have all elements should be the same sign. So this is proved that this is impossible. So this is the exercise. If there are no questions, so let us look at the scaling relations, because for Jones we have scaling relations. So it is necessary to say that it's very simple, but it is necessary to have that for positive Hopf-Link you have Z as Alexander polynomial. For negative you have minus Z. So let us remind what do we mean. So let us be okay. So let us consider this one and say let it be like this. Okay, this is positive, right? Because you have here rotation in the positive direction. So here you have +1, the same here you have +1, and for positive you have the linking number equal to +1. But if we change a little bit, our sorry. No, I mean, no. So this is correct. And here, for this, in order to have what we should, yes, we should make here the direction like this, and you have this rotation. It will be now -1. This is the Hopf negative, where the linking number is -1. The same way, if you will make a resolution of this crossing, you will have -z. So for Hopf, the Alexander polynomial depends whether you have positive Hopf or negative Hopf. So okay. Very good. So to be more careful, let us consider the not. Okay, I should erase this. Let us consider the Alexander polynomial for the not 5, 2. This is actually I'm taking the picture of Raphael with some minor correction, that we consider this crossing, and here, if you look, here we have, I'm sorry, is it okay, or I should make this bigger?
Okay.
Very good. Thanks, Natalia. So I consider this crossing. If you see in the screen, this is overcrossing, this is undercrossing. We are going in this direction. So this is negative sign, right? This is negative sign. And because of this, when we make resolution here, This goes 1 because they are the opposite sign. But here, when you are making smoothing, here is smoothing, you should take minus z. Okay, you should take minus z. 1 is okay. The meaning of the Alexander polynomial of a knot is 1, so it's okay. Okay, so we have 1 minus z with this, but we should look more careful. What is this? This is 1, 2, 3, 4 crossings. There are 4 crossings, and this is really non-trivial, because here we have alternating. Okay, so I make the resolution the same place as Raphael is making. So okay, sorry, no, it's okay. So what does it mean? We're making resolution here to be more careful. This way overcrossing, this way undercrossing. Then we go this direction. Again, this is negative. So when we are making resolution, again 1, if we make this resolution, no, we change crossing, we'll have this object, but now this undercrossing becomes overcrossing, again overcrossing, then it becomes actually Hopflink, right? Because only one okay, you see that there are 2 crossings, but the linking number is I think -1. Okay, so we looking here, but here, as it's Alexander always split in link 0, then here we have z. Here we are making smoothing here. We've get 0, not 0, we have the zone, it's not 0. So sorry, it's a knot, so it's 1. Minus z, it's 1. So let us continue here. Here we have split. This is split, this is 0. But here you have, again, if you make here, you have minus z, because again you have here in this direction, and this is -1, so minus z. So this is a knot, so 1. So what do we have? 1 minus z, and then minus z. So 1 minus z. So we have 1 minus z multiplied by -2z. So it's not like the Alexander polynomial of trefoil, which is 1 plus z squared. It is 1 plus 2, the coefficient meta. So we have that this is 1 plus 2 z squared. Different, and that is the 2 is different from what we get before. we before get 1 plus z squared for trefoil, 1 minus z squared for figure 8. Now we have 1 plus 2 squared, 2z squared for 2 5, okay. The proof for that we considered cinquefoil, the torus not it's okay. His calculation is okay. So let us now consider the Whitehead link. The Whitehead link, the same way I used Raphael's way of calculating. So definitely it is good to resolve here. And what do we have? We have again this direction. This is overcrossing, this is undercrossing. So we have minus. If we have minus, then we have 1. So if we change crossing here, then we definitely have 2 unknowns splitting link, 0 Alexander polynomial. Okay, then because it was minus, then we take minus z. Minus z, what will happen? This is true, the same as Raphael's calculation. Smoothing gives you 3-component link, like analog of Hopf, but with 3 components. So each of them, maybe not this one is this unlinked, but each red and black, it is linked. Minus z of this stuff, and let us make resolution anywhere. For example, here, what do we have? If we change crossing here, by the way, I should say that here that okay, this is the previous. This is not our actual. This is previous stuff. We are looking this crossing. This is overcrossing. This is undercrossing. Arrows. So we are moving in this direction. This is positive. That's why we take positive sign. And then Z is in positive sign. But if we change crossing here, we liberate this unlink. It goes here. I'm not. It goes far away. So we have, it's not maybe true. It's link here, but anyway, it's split. Then it gives 0. Its impact really is 0. So we should make 0, 1. 0 with coefficient 1. And here, because 1, we should have this thing. And this is nothing but our wonderful Hopf that we considered. And if we look now, this is negative Hopf, because if we go this overcrossing, undercrossing this direction, then this is negative. So the negative Hopf we should take with the sign minus z. Okay, so this is This is, no, sorry. So, excuse me, I clicked. That. We get this. And so what we get here from here, 1 gives 0 minus z plus z. This gives again 0. This gives again 0 minus z. So finally, we get z cubed. So this is the z cube we get for Whitehead link. And this is another story. Also, it differs from our previous stuff. See, it's different, for example, with the Hopf link, where we have plus minus z, and here we have z. Okay, but anyway, the linking number. Other questions? Remarks? No questions? Let us continue. What is left? It's Borromean stuff. Borromean stuff is much more work for our calculations for Borromean rings. So the same way, let us take the highest. You can see, you can check whether I made a correct picture of Borromeans. I think so. If you see remarks, please say me immediately. Tell me immediately if you have remarks, okay? So we take this crossing, again, overcrossing, undercrossing, negative crossing. So we have 1. When we change crossing this, we change overcrossing. The blue one goes over. And here we have smoothing. Then what this smoothing has, it's wonderful. Look, the red one say it's the blue one. Okay. There were 2 components, becomes 1 red component. If I read this correct. So maybe this you should make. Okay, so you have this link, 2-component link with 1, 2, 3, 4 crossings. Okay. As it was minus, we take minus z. But this is not split as we had before. Then we simply consider this with number 1 before. Okay. So let us look forward. Then we consider, for example, this crossing. What do we have? This overcrossing, this undercrossing. It goes this direction, then it is possible. Positive, sorry. Positive, then 1 as usual, and z because it is positive. Then if we change here, I didn't draw the picture, but it is evident that if now blue becomes overcrossing, it is overcrossing everywhere. And the blue ring goes far away, so it splits. I wrote, sorry, this ugly writing, splitting. So it splits. Okay. It splits, and then it doesn't matter. It's 0. And Z, because we had, and a little bit, you should be more careful, because now I wrote, for to be different, I wrote that now blue, because it goes from blue to red. Blue eats red. Blue eats red. Okay. Am I right? Yes, because you should go here and you return. So blue eats red and becomes this wonderful thing. Okay. So Z with this. Okay. Yeah. Look what will happen here. For example, we are changing here. We're changing here. Here it is this way, and then this way it will be positive direction. Then that's why Z. Positive 1. Here we get our wonderful hopsling. Here we have this stuff. So what it will be when we are making smoothing. We are making smoothing now. The green one eats the red one. You have this link like this. Actually, it is yeah. And we can so this is 1, 2, 3, 4. So if you have alternating link, this is actually the knot. Alternating knot with 4 crossing. This is definitely figure 8 knot. So minus Z squared multiplied by Z, but this we're using our previous calculations. This is 1 minus Z squared. So this will be the impact of this knot. So here, what do we have? Here we have our Hobbs link negative, so minus Z to here. And finally, what do we have? Minus Z here and minus Z here, so finally plus the Z squared. So here plus Z squared. Again here, again Hopf and minus Z squared. So what do we have? Minus Z squared plus Z squared plus Z squared minus Z squared plus Z4. And we get our final result that it is Z4. Borromean links, Alexander polynomial Conway is Z4. So we shall make for germs today, I suppose, the same thing. So other questions, remarks for that? This is the standard type of skein relations. Only for Jones they are much more complicated because the skein relation is it's also not very complicated, but not so elementary as for the Alexander. Okay. If there are no question, we go to the exercise number 10. So maybe we shall not pay a lot more attention to this. I remind that our braid relations was like this, and commutating like this, and commutating with the sigma I, sigma j far away, the close they have the following relation. So and Artin himself also showed that it is possible to make the following presentation with only two generators. So we consider sigma 1, and we consider sigma, and so the geometric presentation is sigma 1, sigma 2, sigma n, and so on. Here we have only two. So Natalia, maybe you want to have some remarks on this exercise?
No.
Okay, so what do we have here? How can we go from sigma 1? We have standard sigma 1, sigma 2, so on, sigma n minus 1. Here we have only two.
Sorry, can we draw a line?
Which one?
This is a braid group, and
Right.
we can draw a line. And what is this generator?
Yes, this is my aim to give this, maybe not in lines, but we can draw, no problem. Yes, exactly. Tatiana, maybe you can help us how to come from what is sigma? Tatiana, are you with us? So sigma is equal to sigma 1, sigma 2, sigma 3, so on, sigma n minus 1. Okay. So you can easily draw the picture. What is this? So I should find the free space. So for the three strands in braids you can see everything for this is sigma 1, right? This is sigma 2. Okay, so this is simply sigma, nothing special. In this case, sigma is the following. Or if you want to consider 4 strands, okay, I shall try now to write down, sorry. Okay, let it be here. Sigma 1, then sigma 2, sorry, sigma 2, sigma 3, this is sigma. Natalia, is it okay? So this is sigma. And this is the, okay, I'm listening.
I have problem with sound. Repeat the last couple of minutes.
Okay, so Tatiana, we are considering this presentation for the braid group. The presentation which is economic from the point of view of generators. Do you hear?
Yes.
So we consider the following presentation, which has only 2 generators, sigma 1 and sigma. The question was how to depict sigma 1 is just the same usual sigma 1. So I even keep the same notation. It is nothing but if you have, sorry, if you have here your standard braid group, you have sigma 1 and you have parallel strands. So this is sigma 1. And in order to go to sigma, we make the following definition of sigma. It's nothing but the product, consecutive product. We are considering consecutive product, sigma 1, sigma 2, sigma 3. This is the picture for sigma for the 3 strands braid group. And this is for 4-strand braid group. Sigma 1, sigma 2, sigma 3. Okay? Do you hear, Tatiana?
I understand.
Oh, very good. Very good. Say, for example, why? I don't want to give all the calculation. It may be too boring, but just to say why these two guys, they generate the braid group Bn. Here we used very many actually, but here only two. For any n, you can take the two generators. So how we can see, for example, that other generators can be expressed by only two of them. For example, the following formula: sigma I plus 1 is equal to sigma in degree I, sigma 1, sigma in degree minus I. So, by the way, why did I make this make this exercise? Because it gives you understanding that all the generators of the braid groups, they are conjugate. So they are conjugate, of course, they are conjugate to sigma 1, so they are conjugate between each other. All the generators for all I equal to 1 and n minus 2, okay? All the generators of the braid group, they are expressed by this formula. So maybe not for all complete calculation, but just let us make a calculation for sigma 2. Why sigma 2 is expressed by this formula. Let us take sigma, because here is 2, then this is 1. Sigma 1, sigma minus 1. This gives you the flavor of the work of generators and relations in the braid group. So so do you see this line?
Yes.
You see?
I see.
Please tell me if you don't see this, because it's calculation.
Maybe
Sorry?
Upper.
Yes, this one. Do you see?
Yes.
Very good. Because in braid groups, details are matter. So how to prove this? What does it mean? It is sigma 1, so on. Okay, I'll write down sigma 2, so on, then sigma n minus 1, sigma. Now, if you write this one, minus 1, then you need to take the reverse order. Sigma 1 minus 1, blah, blah, blah. Sigma 1 minus 1. This is sigma minus 1. and in the middle, sorry, I forgot to write sigma 1. This is very essential. Look now that these guys, all they commute sigma n minus 1 commute with sigma n minus 1, etc., etc. Just for sigma 2. For sigma 2, because it is not commuting with sigma 1. So what do we have this equality? Sorry, I'm looking for the spare place. It will be sigma 1, sigma 2, sigma 1, sigma 2 minus 1, sigma 1 minus 1. This is what is rest from this formula. Because of the commutating braid relations, the intermediate terms, one kills another. One kills another, and only sigma 2 is sigma 2 survived because we have this stuff. Okay.
It's equals sigma 1.
Sorry?
It's equal to sigma 1.
This? No. No.
Sigma 1, sigma 2, sigma 1 equal to sigma 2, sigma 1, sigma 2. And
bravo. By the way, as I see here, we can switch to Russian. Dear friends. Наталья.
Да?
Можно перейти на русский?
Да, если мы не боимся по-русски выкладывать потом запись.
Это да, это да. Это
For Рафаэль.
Да. Это хороший, да. Рафаэль болеет. Окей, да. Виноват, я об этом не подумал. Okay, so let us continue in our foreign language. So, yes, Tatiana, you are great. This example, why I gave this exercise? Because here you are using braid relation. You have sigma 2, sigma 1, sigma 2, okay? And here we have exactly these two guys squared, inverse, okay? So you kill this one, and this one, this one, and this one, right? So it gives you sigma 2. What we need. Very good. Very good. Okay. So you have the we can now you see how we can use this proof by induction, for example. How we can prove this by induction, because we prove this for sigma 2. Then what do we have? We take 1 from here, sigma minus 1. Here we take also 1 from here, and here it will be sigma 2. This is what we've done, sigma 2. And the same way by induction, we prove that this for sigma 3, for example, and so on. So this is so the final proof. So I take only the idea. I say only the idea of this stuff. So yes, if there is a okay, I can use. Okay, very good. So okay, now it becomes now it became free. Now the usual standard use of Titze transformation. You have, say, for example, you have the standard. You have standard presentation, generators, and then relation. Then I add new generator and new relation, that sigma is equal to sigma 1, sigma 2, sigma n minus 1. Right? So it is possible. This is exactly Titze transformation. You add one more letter, and this letter is expressed with the help of the other generators. So it is possible. Now, because we have relations that we've proved relations, so we can use these relations, that sigma r is equal to this. Then it is what is rest. It is necessary to rewrite relations that were to rewrite the braid relations. To rewrite the braid relations in the new generators, and we'll get these two relations. So this is the scheme, esquisse, if you want, of the proof of this exercise. I think we shall not spend more time on this, because another one is to construct the inverses. To construct inverses for our generators. So I remind that we had relations. No, sorry. We have no. Excuse me, please. There were sigma i's that were the automorphism. So I remind that x I goes to x I plus 1 and x I plus 1 goes to x I plus 1 minus 1 x I plus 1. So we used that this is automorphism of a free group. So in order to prove this, the best way is to construct opposite. To construct opposite. That means to construct this. This is what sigma I itself, and to construct opposite direction. So what can you propose as the opposite homomorphism in verse 1? Somebody wants to tell something, to say something? Natalia, do you want to say something?
No, okay.
Diana?
No.
So it is evident that if x I plus 1 is the image, then we simply should make that x I plus 1 should go to xi. Okay? Because we actually need to have opposite homomorphism. Xi goes to xi plus 1, then xy goes to xi, because we need that xi should be identical here, right? This is evident. Then look, what should we change? We should change x I plus 1 should go to xi plus 1 to go here. Okay, I continue here, it's simple. But xi plus 1 is already, image is defined. So it is xi minus 1. This is defined. We should know what should be the image of this. Our aim is to know the image of this. But image of this is also defined. It is xi, because of this one. So what should be in the middle? What should be in the middle such that xi plus 1 should go to x plus 1? So it should be xi, right? In order to kill this, then xi plus 1, 3, plus 1. And in order to kill this stuff, there should be xi minus 1. So image of xi should be the following. So image of xi should be xi plus 1 xi minus 1. That's all. So this is the answer on this question. Other remarks? Tatiana?
А там индексы правильно стоят, вот где у вас подчеркнуто? Там x и-то в минус первой?
В конце, да?
Сейчас. А, это просто минус 1, это относится к x и тому, которое...
Да, да, это
всё.
за счет того, что я мышкой плохо
Все,
пишу.
поняла. Ага. Все, спасибо.
Thank you very much. So this is, if there are no questions, then we finish this stuff and we shall look the following wonderful theorem. So the following wonderful theorem is that it was actually proved by Artin also in his initial work, the same work in the as where the presentation that we discussed in our first exercise. So the following theorem, that let beta be the element of the braid group. Okay. So let us say here. Let beta be the element of the braid group. We can depict as Natalia asked to depict it the following way. And let in the box there will be a braid, right? And there are strands that are growing here. And we denote by beta hat the closure. Excuse me. Right. So this is beta hat, this object. This is linked. And now we want to calculate its fundamental group. So we take the point somewhere outside and we consider the fundamental group of this object, which is obtained by the braid beta. But the braid beta had also another side. It is what we discussed. It is the automorphism of the free group. If this beta belongs to Bn, this is the free group of Fn on n letters comes into the game. So beta is automorphism. I make even the same notation, beta. Now let us consider the following group. You write the presentation of this group. You write down n letters, the same number as in Fn. Okay. And you write down relation. Maybe n relations, better to say. Xi equals to beta acting on Xi. So beta is an automorphism. So beta, so we considered ours supposing that you are computer. So computer transforms the letter I to some word on X1, etc. N. Right? So word I. So this is a word. This is this word, right? And here you have 100% presentation of a group. It gives you the finitely presented group with n generators and n relations. And the theorem is that the group of this link, in general, you know, it may be linked, that the group is exactly this group. This is the wonderful theorem. And as interesting theorem, it takes into account, it involves several things. This is geometrical braid. This is the link defined by this geometrical braid. This is the fundamental group of the complement of this geometrical link. And this is a group which is given by this presentation as given by generators and relations. So several things are taken together, and this gives you the theorem. Other questions? Okay. So I suppose that you've seen this theorem before, but now we shall use this theorem in order to calculate some concrete things. For example, n component unlink. We have n component unlink. How should we calculate the fundamental group of it? Natalia, you have ideas, I suppose.
We have n generator.
Right?
Free group.
Oh, yes, and why?
Let us take trivial braid.
Absolutely.
And trivial morphism.
Equal to 1.
Do we have a trivial morphism?
Yes, and what kind of relations do we have?
And we have relations xy, xi is equal xy.
I.
Xi, yes.
Yes. So we have tautological relations. Nothing interesting. So in this case, we simply can say that we have essentially empty relations, right?
Yes.
So and this is exactly the presentation of the braid of the free group. Absolutely. We have that in our case, this is nothing but Fn. Very good. Excellent. Thank you very much. Bravo. Other questions, by the way? Tatiana? If no question, we consider hot links. So what should we take? Tatiana, are you with us? What braid should we take in order to consider hot link? To get the group of the hot link.
Maybe abelian group.
Right. But how can we get it?
Let us take sigma 1 square braid.
Let us take sigma 1 squared. So, okay. We take our braid. Sigma 1 it's enough. So, sigma 1.
Two line and sigma 1, sigma 1.
Right. I'm trying to make pictures, right?
Yes, and this is a hop link, okay?
This is a hop link, sigma 1. So sigma 1, we should start with 2 generators here, right? Suppose that n equals to 2. So what should we have? We should consider sigma 1 squared. It is x1 goes to x2 and x2 goes to x2 minus 1, x1, x2, right? This is the action of sigma 1 squared on x1. Action on x2, sorry, I write down here. x2 goes to x2 minus 1, x1, x2, right? Now one more. What does it mean? x2 goes to x2 minus 1, x1 minus 1, x2. This is this. Then x1 goes to x2. Sorry, I continue here. And x2 again goes to x2. x2 minus 1, x1, x2. Then this and this disappears. So what do we have finally? x2 goes to what? x2 minus 1. x1 minus 1. x2.
Sorry.
Yes.
If we consider complement of the Hopf link in sphere,
Yes.
and the torus is known to be abelian, and its intuitive point
Yes, I agree, but I want to use this theorem. The aim of this exercise was to use this theorem, Tatiana. I agree with you that maybe simply.
I think it's clear, and maybe we can't take theorem.
Yes, it's clear for you, but I just want to use theorem anyway. So you see, what do we have? The first relation is the following. x1 goes to this one. The second relation is that x2 goes to this one. So what does it mean, the first relation? The first relation, x1 equals to this one. So we can rewrite this relation. It should be x1, then multiplied by x2 to the left, it will be x2 equals to x1, x2, right? From this, we have x1, x2 here. And actually, this one is again the same, because if you already have this relation, you get actually the same. Is x2, and you get the same relation. So you have two generators, x1, x2, and two relations that actually the same relation, x2, x1, x1, x2, and this is commutative. So we get that for Hopf link is commutative. Okay? So Tatiana, you agree?
Yes, I agree.
Thank you. So, and the last one. So we should do this more quickly. Otherwise, I will not have time to speak about John's polynomial, which will be a pity. So anyway, let us consider trefoil, our wonderful trefoil, to get again braid relation. So today is the day of braid relations. So let us consider trefoil. Maybe I'm stupid. We need this. We need this because okay. Anyway, I'm stupid that I erased this. Anyway, so trefoil. What braid should we take? Natalia? For trefoil?
I think.
Yes, very good, very good. Татьяна? Какую косу взять?
Мы группу ищем?
А?
Группу ищем? Или что мы делаем?
Мы ищем косу, из которой получить трефойл.
Я найду купон магазина кексиков. Я отвезу нас туда на моей машине. Афина, что ты вечно про суп? Давай про купон.
Идет?
Braid group.
Yes, the braid, which is equal to sigma 1 cubed. If you consider, oh no, maybe bigger.
Это потому, что ты притворяешься кроликом. Тебя никто не спрашивал, Энди. Спрей мне получить вишенку.
Trefoil?
Это сложно. Просто не получается.
Just consider that you have alternating links with alternating link with 3 crossing. No other possibility. What is trefoil? Trefoil is an diagram of trefoil is alternating diagram with 3 crossings. Figure 8, alternating diagram with 4 crossings.
Okay, let's try take 3 line and sigma 1.
So maybe I okay, so you should put crossing under crossing anyway. But for example, now, Natalia, you cut here.
Cut.
You cut.
Free cut.
No, just cut here. You have. Возьмите ножницы и разрежьте вот так, а потом распрямите.
Только в одном месте.
Да, только в одном месте вот здесь. Ну, в смысле в 2. Я имею в виду, линия идет одна. Допустим, у вас есть центр.
Окей.
И потом разверните, и у вас получится, вот вы разрезали, да? You cut there, and you get, they are rotating, but you have exactly this picture. You have exactly this picture. And here you cut, or you can go opposite way. Say you take your braid and now join this with this, join this with this, and you have exactly this trefoil. Okay? Can we continue, Natalia?
One moment.
Yes.
Okay, we have 3 sigma 1. Okay?
Right.
Sigma 1 cube. Okay?
Say this is first sigma 1, this is second sigma 1, this is the third sigma 1. Only in that picture, they are grouped around. And in that picture, they are in one line.
Okay, I see. Thank
Very
you.
good. Very good. So now let us continue, because we had, now again, we have, this is the simplest case. We have x1, and we calculated the first step, the sigma squared, sigma 1 squared. It was x2 minus 1, right? x1, x2, like this. And for x2, it was more complicated. It was x2 minus 1, x1 minus 1, sorry, this should be x1, x2, x1, x2. This is what happens if we apply sigma 1, 2 squared. But we need sigma 1 cubed. So one more application of our favorite sigma 1. So what does sigma 1 does? Sorry. So I erase this one to have a space. To have a space. So what do we have?
Sigma 2.
Sigma 2 minus 1. Sigma 1, this is 2, minus 1. Sigma 2. And sigma 1 again goes to sigma 2. Sigma 2 goes to sigma 2 minus 1. Sigma 1 sigma 2. So these two guys disappear, right?
Right.
What do we have? X1 equal to these guys. And this will be, if we now take multiplication by the left, x2 by the left, and then x1 by the left, what do we have? x1, x2, then x1, our native x1.
We have x1, x2, x1 is equal x2, x1, x2. Yes.
And I don't.
Right.
Yeah. X2, I feel x1, x2. So I don't want to lose time. You will have the same relation here. The second one, it will be a little bit more complicated, but again, you have the following thing, nothing more. So you are getting, using this theorem, you are getting, I think this is simpler than Wirtinger, because Wirtinger we have much more job. Tatiana, do you agree? Okay. So this is what we have, and also some other wonderful topic is related to, which is related to braids. This is the presentation of braids by matrices. So if you don't have questions, I'm passing to matrices. And sorry. So, of course, braids are good from geometrical point of view. But for example, if you want to manipulate with braids by your computer, then probably you need to know whether your whether your braid can be represented as a matrix. So now let us consider the following matrix. Let us consider the following matrix. So it means I switched notation to, but I think maybe you understand. So this is the unit matrix. In the previous one, in the previous sheet of exercises, I use another notation. By the way, Natalia, is it usual notation for unit matrix for you? E, or you are more accustomed to I, say IN? Okay. Anyway, it's okay. So now, let us consider the following matrix. The matrix is belongs to the matrices of the following ring. You have Z, T, and T minus 1. So Laurent polynomials. you consider polynomials of positive degree and negative degree. So it's a little bit larger ring that our ring Z. So let us consider the following matrix. The question whether it is invertible. You should take this is matrix is divided by blocks. So this is the unit matrix. Evidently they are invertible. So by the rules of operating with block matrices, you only need to know how to make construct inverse of this matrix. So if you calculate the determinant, it will be T, and so T is invertible. So the matrix is evidently invertible, right?
Maybe minus T.
Right, exactly. Yeah, absolutely, minus T. I'm sorry, I'm in a hurry. I want to say about John's polynomial. Sorry. Yes, you're right. Minus T. It's an excellent idea. So how should we now construct? Actually, we need to construct a block for this. So we shall divide by minus T. So how can we construct the inverse for this? Natalia, can you write down the inverse for this block 1 minus T, T, 1, 0? How can we construct the inverse of this block? We know that the determinant is minus T, so we can do this.
One moment. Okay.
Yes.
0, 1.
Can you write down? You can, I think, use the screen somewhere.
Okay. Maybe yeah. Okay. Okay.
Mm-hmm.
Sorry. I think that's all right.
Okay. So now, can you can you try at least some entries, or maybe we have no time.
Maybe sign.
No, this is okay. This is 0, then yes, it should be.
No.
Okay. This
This sign is okay, so yes. Right, in order to go. Yes. Very good. Very good. Very good. Very good. Very good. So, okay, so can we now make at least some attempt to prove that UI, actually we can do this in, it's sufficient to do matrices 3 by 3. So say U1, U2, U1 is equal to U2, U1, U2, U1, U2. So make this calculation.
Это очень сложно.
Okay, let us skip it. Let us skip it. This is calculations of matrices, so let's skip. Very good.
Okay.
But I can only say that it is true for all, and then you can make a homomorphism. You can make a homomorphism. Sigma I goes to UI, and sigma I goes to UI, and then it defines a homomorphism from Bn to G matrices G, L, N, Z over T E minus 1. Sorry. Okay. So it defines a homomorphism because the relation is satisfied, and this defines a homomorphism. So it was defined by Werner Burau in the 30s of the last century, and it was proved. Actually, our exercise that we discussed you can use this in order to prove that for B3, this is a monomorphism. So it means that this presentation, the group of braids on three strands, it is exact. So B3 is a group of matrices, actually, subgroup of matrices. For Bn greater than 4, strictly greater than 4, it is not a monomorphism. It was proved not long ago, and this is not, it has very small, but anyway, it has a kernel, non-trivial kernel, right? And for B3, B4, this is a classical fact. B4, it is still unknown. It is still unknown whether this homomorphism is a monomorphism or not. But it became not so interesting question because it was defined another homomorphism into another bigger ring of matrices with more parameters here than the braid groups is that there is injection, but not for this exactly. This was done by Werner Burau. It is called Burau presentation, Burau representation. Okay, and the matrices where generators sigma I are much more complicated in order to construct exact representation of the braid group. Okay. Other questions? No questions? Okay. If no questions, we can speak today a little bit about John's polynomial, right? No more questions, dear friends?
Yes.
So John's polynomial. This is an interesting stuff. So I don't know why. The screen goes. I don't know. I don't know why screen is going. Excuse me. I'm trying to. Yes. You see? You see the screen, Natalia, Tatiana?
Yes, I see.
I see.
Very good. Thank you very much. So, John's polynomial. John's polynomial was first constructed by Jones, and it was constructed by using the Markov theorem. If you remember that it was using the braids, and he constructed another representation of braids in some algebra, and then using the trace over the algebra, you know, the trace of matrices AB equal to trace BA, and this corresponds to the first Markov move. So he he sent braid group to algebra, use trace. Trace corresponds to, in the trace he used, trace actually satisfies the Markov moves, so it's okay. And then you need to satisfy, to make some job to satisfy the second Markov move, and this works. So it was constructed by this using Markov theorem, but proof that I try to give here is much more simpler, and so it happens that proofs which are going later are. So we give the Jones polynomial the same way as Alexander polynomial by the Skene relations. So axiom 1. To each oriented, again, essential word is oriented. Remember that for hop link, we get other orientation where we get negative linking number, we get another Alexander polynomial. The same way here, oriented. Oriented is associated Laurent polynomial. So the notation are traditional notations that are taking 1/4, 1/2, sorry. It considered to be the standard stuff like to use this E1/2, the square root of the variable. Okay, so the first axiom is simply saying that this is a link invariant. So if our links are equivalent, say Rademeister move, isotopy, homeomorphism of ambient, so it means that the Jones is the same. So this is completely the same as Alexander Conway stuff. Absolutely the same. And you can also Alexander consider as polynomial here. Okay, so the first one is okay. Then the second one is the same, that trivial gives 1. And the third one, again, we are considering the Skene, so we are considering our favorite Skene diagrams, so that we have L plus link which the same rule, L plus, L minus, and L smoothing. So we consider them, and this is the Jones-Skene relation. So you see that this is different. So if you if you skip, for example, these two things, these two stuff. So if you take away these guys, just 1, 1, this will be up to variable. It will be the Alexander Conway stuff. But here we have this, and you see when you are working Skene trees, then these guys are essential that you, when you want, for example, to solve the positive crossing, then you have you should multiply by t, and here you have already t squared, and here you have a little more complex. So if you don't mind, I have a cup of tea. I have small problem. You don't mind? 5 minutes, I drink a cup of tea. Okay?
Okay.
Can I continue?
Yes.
Yes.
Very good. Very good. So this is the scale relation for Jones polynomial. So there are another variable, and you'll understand in a moment why this is a good variable. So in the Kaufman variable, you take variable A, and Jones polynomial becomes in the following form. And recently, Jones polynomial was generalized to Havanov theory. In the Havanov framework, it is necessary to make some changes. So the trivial knot takes, of course, sorry, the variable should be different. So it is intermediate between Jones 1/2 and A of Kaufman. So it's variable Q. And also for the purposes of Havanov theory, it is better to take that the trivial link is having the following invariant, Q plus Q minus 1. So for Havanov, it's a bit different scale relation. So Q minus 2, Q2 equal to Q minus 1 minus Q. So then why the Jones is so interesting? Because it has the following property, that if you consider the mirror image, then you should make you should put T inverse, and then you will have the Jones polynomial for T. So you have substitution like this, and so this gives good possibility to calculate the Jones for inverse for the mirror image. So I would like to present the Kaufman approach to Jones polynomial. So Kaufman approach was later. In some sense, it is like if you know the answer, you should construct something knowing the answer. At first, let us define that the two diagrams. What does it mean that diagrams are regularly isotopic? So it means that they are almost ambient isotopic, but without type 1 Reidemeister move. So Reidemeister move type 1 is forbidden. So the Kaufman bracket we construct for K. Now we forget about orientation. We say that let K be link diagram. K just a diagram, so it's not isotopy of link for only for diagrams, and then we improve our bracket for to construct invariant at first of two Reidemeister moves. So the first, the first is trivial. So in the sense that trivial knot is gives better to say not to not, sorry, diagram. Just consider the following diagram, just a circle. It gives you 1. If you have diagram which is composition, this better to say disjoint sum of a knot and something which is not empty, then it is the same as the invariant, the bracket of K multiplied by D, some D. I forgot to say that. K is the element of the ring. We consider the ring of 3 variables, A, B, and D, starting with. And then our scale relation, but to say Kaufman scale relation, is the following. That if you have crossing, this is guys without orientation, then you not considering skeins which are usually with given orientation. You just smooth 2 ways. You smooth here like horizontal lines with some coefficient A, and vertical lines with other coefficient B. B, A are given here in the definition of our ring, okay? So you see that, what is it? It is no sense invariant on the Rademacher moves, because why should this bracket, this element of the ring ZABD, be invariant? No reason to be invariant under Rademacher moves. And so we shall consider it on the diagrams, and we'll understand what conditions should be given for A, B, and D in order to these things should satisfy 2 and 3 Rademacher moves. So we are looking only for 2 and 3 Rademacher moves. So our purpose to make that this bracket should become invariant under 2 and 3 under Rademacher move. So 2 and 3 Rademacher moves, it means, what does it mean? We shall see in detail. So the axiom 1 means that the gives value 1 on the trivial. The axiom 2 gives that you should multiply. If you have somewhere unlink, you may escape, and but you should multiply by some variable D. Okay, and 3 means that the diagrams are locally the same, okay? Okay, the small remark that every crossing we can smooth. We can smooth every crossing, and we reach finally the diagram which can consist of disjoint union of circles, because everything is bounded, and there are no crossings. So what does it mean? You can simply have several circles. Okay. So this means that if you have several, if you finally get the several circles, then k should be d raised to the n minus 1, the number of circles. So, right, because one circle gives 1, and then 2 circles will get d, and so on. So sorry. So, and that's why this reason why in Havana's theory it became more convenient to see that if you have n circles, then the invariant should be equal to d to the power of n, not for the circle given to 1. So the circle should be d. This is nothing but some convention. Okay, so then something I simply wrote down because it's too painful to make this in Czech. Then I simply made a photo for you. I'm sorry. Excuse me, I'm trying to make it more, but I don't know how to move it. Very good. Do you see the screen, Tatiana?
I see.
See my handwriting terrible, you see?
No,
I
handwriting, no.
You don't see?
I
Lemma 1.
don't-
No, lemma 1, no.
I see rules 2 and 3.
Now, you see?
Yes, I see.
Yes?
Yes,
Lemma 1?
yes, lemma 1.
Very good. Sorry. So, this is how to make the invariance. So, lemma 1 means that the following formula. Look, our aim is to understand Reidemeister 2. You see this is for the Reidemeister 2. What Kaufman is doing, he uses the formula with A and B. He smoothes this and he obtains the following formula. Then in order to satisfy Rademeister 2, it should be that AB should be equal to 1, and this thing should be equal to 0. Okay? This is the force, by force he's doing it. So he just considers the smoothing. Right? You see, he considers the Kaufman bracket of this guy, and he makes smoothing at first in this point. You see? You see this Kaufman bracket, Natalia?
Yes, yes, I see.
Very good. You make smoothing here. What does he has? A parallel line here and smoothing here. We have a loop here. B, we are smoothing here vertically. So this line goes here, and then we are making smoothing only in one line, 1 point, sorry. This one and this one. So this is nothing but smoothing in the upper point. Okay? So now let us make the smoothing here and here. You have 2 crossings in what is left. So then again, we're using Kaufman rule. So I remind you, Kaufman rule, no. Kaufman rule, where is Kaufman rule? Aha, this is Kaufman rule. We are using this Kaufman rule. The crossings, horizontal A, vertical B, okay? Nothing especially interesting. So we have now 2 crossings. We have the small algebraic stuff. Then we have here A and B and the circle inside. You see the small circle?
Yes.
Very good. So small circle, it means that D should arise. Small circle and D should arise, because if you have diagram and you have small, you have circle, anyway, small, not small, doesn't matter. So you can take away, but then you should leave these 2 horizontal lines. So this, and this, nothing but Kaufman smoothing several times, and you see that Kaufman bracket of this diagram is equal ABD plus A squared B squared, 2 horizontal lines, and AB here, AB here, right? BA here, vertical lines. Our aim is to have vertical lines. So what does it mean? We get what we need. A, B should be equal to 1, because if AB should be equal to 1, this will be Rademeister invariance under Rademeister 2. And this term should be equal to 0 because of the same Rademeister 2. There are no horizontal lines in Rademeister 2. So this should be 0. So you see B equal to A minus in the degree minus 1, and D should be equal to this one. Then you should AB equal to 1. Then simply D should be equal minus A squared minus A minus degree squared. Okay, so this is if you now have this condition, AB equal to 1, D equal to minus A squared minus A minus 2, then your Kaufman bracket should be invariant under Rademeister 2. Clear?
Yes.
Tatiana?
Yes.
Very good. So I need to put second sheet. Very good. Right. Then miracle comes. You need not to look at Reidemeister 3. If these two conditions are satisfied, Reidemeister 3 is satisfied automatically. So the lemma is the following, that type 2 Reidemeister for Kaufman bracket implies invariance under type 3. So the proof is also elementary. What do we have? We have this thing. Now we make resolution. We make resolution at this point, A and B. So horizontal, vertical resolution. But now we simply move this branch is under, we are moving it in space. We are here, no problem. Here, Reidemeister 2. You see? You Reidemeister. Sorry?
We used 2 times Reidemeister moved type 2.
Right, exactly. Exactly. First one we put, absolutely, Tatiana. So first time we put it here. This is the first time Reidemeister, and the second one we put it here, and this is exactly what we have. Here is nothing but isotopy of diagram. You are not changing the crossing picture of this diagram. So here exactly 2 times Reidemeister 2, and so to make a resume of this, we say that if you have this AB equal to 1, D equal to minus A squared minus A minus 2, so we have invariant under regular isotopy. Why it is called regular isotopy? Because it is not invariant. So isotopy should be regular in this sense that if you consider this stuff, it's not equal to this, or probably it's right. So it's not equal to this. So what is the geometric interpretation of this? Imagine that you have a ribbon, that this is a ribbon, not just a line, but this is a ribbon. So, and it is a ribbon, and the width of this ribbon is looking for you, or vector, any way you want. So it's not just line, but a ribbon. And when you are making this to go to this, you need to make a rotation. You make to make this equivalent to this, you make a rotation, and your ribbon will not be a trivial ribbon like this. If you're considering this like a ribbon, this is 2 different ribbons. So if you consider ribbon knots, then Kaufman bracket is invariant of the ribbon knots. It is not invariant under Reidemeister 1. So this is the specificity of Kaufman bracket. Invariant under regular isotopy, not invariant under Reidemeister 1. Okay.
Vector bundle on this line. Okay.
Sure. Framing. It is called also framed links. You can consider, yes, you can consider in this point that vector is looking for you, for example. It's called blackboard framing. All the time vector is looking for you. When you need to go to this, then you need to rotate, and then vector which was looking for you becomes to looking to the opposite side of the blackboard. Okay. Yes, exactly. Thank you very much. Thank you very much. So this is the Kaufman bracket. This is Kaufman bracket, which is invariant of two types of Reidemeister moves. Okay, and okay, again. Yes. Now we can move to, if we now have this convention that B is equal to A minus 1, and D, what was in the axioms at the very beginning, D is equal A minus A2 minus A minus 2, then we have the axioms for the Kaufman bracket, which is invariant under regular isotope. So now how to, and Kaufman bracket is invariant, which has its value for itself. But if we now want to look at John's polynomial, we need to fix Kaufman bracket, which is not invariant under the first Reidemeister move, and what is, how to fix this? We need to do something with this stuff. This, and to fix this, we need to look at this, what is for the diagram, the rise. The rise is exactly this. For example, if you have here this direction, what do we have? Then the rise of this part of this crossing is equal to +1. Rise is equal to +1 because we are going in this direction. And the rise of this, so what is the rise of this? You have here now rotation in negative, you have rise -1. Oh, and the total number, so the same way as you were considering the linking number, but linking number we were considering this rise of different components. But here you are now taking rise everywhere. So this is the rise, and now we make the following correction term for our Kaufman bracket. So suppose that you have diagram K and diagram K. You take orientation, because rise is defined only for oriented stuff. You consider Kaufman bracket of K, but it means that you forget about orientation. This is well defined. But here, the rise has its own right, and you make this correction. You make this correction. And the theorem is the following, that the polynomial, which is now takes values in a minus 1, as Kaufman brackets takes values there, and you simply changing a little bit, you are making some correction term which takes into account to satisfy the Reidemeister move 1. So the theorem says that this object is now invariant, isotopy invariant. So it was Reidemeister 2, then 3. So sorry, I make a lot of misprint. It is invariant 2 and 3, and this term, which is a minus 3 rise, is correcting that the object becomes isotopy invariant for oriented links. So, and now what is rest? So you see now, for example, if you see the definition of Kaufman bracket, what do you can say that you use the definition of Kaufman bracket? So let K prime be the mirror image of K. Then by the definition of K of Kaufman bracket, you simply interchange A and B, horizontal, and so if you're changing the crossing, then you have that Kaufman bracket K of A becomes the Kaufman bracket K of A minus 1. And the same way this one becomes the W, it becomes the right. For the rights, it is also taken into account. The minus goes to plus. So you have that by construction of Kaufman smoothing, you have that mirror image. For mirror image, you simply should change variable to its inverse. And then if you now make the following change of variables, so Kaufman has A, and now you substitute T minus 1 over 4, you will get the Jones polynomial. You will get the Jones polynomial of, and so this is as far as I know, this is the simplest way to prove the invariance of John's polynomial of Reidemeister. So, okay, we have no time to make some calculations that I prepared, but I can simply tell you can play yourself. Excuse me, I look where I wrote down the yes. So so I can write down that for the Jones polynomial for Hopf positive, it has the value minus E5 right. Over 2 minus D 1 over 2. This is positive Hopf. Negative Hopf will have, of course, minus 5 over 2 minus T1 over 2. For trefoil, I just look my calculation for. Okay, I see. First, I see figure 8. We don't have much time, so by figure 8, I say it's beautiful. So T squared minus T plus 1 minus T minus 1 plus E minus square. You see, we saw that figure 8 is Amphicarol. So you see here, if you are changing T to T minus 1, the polynomial is the same. You see? John's polynomial is the same. So this is what we saw in our exercises when we were considering the how to move figure 8 knot to its mirror image. Sorry, I'm looking for maybe my calculation that I wanted. So for the trefoil, wonderful stuff. Sorry, I just look how to get the trefoil. And you see, just a moment, sorry. So, as far as I remember, T4, I should remember the signs, E3 and T. Then the signs I should remember. Yes. You can use the trees which we used for today, not today, in the previous lecture we used for calculate the calculate the Alexander. So
Plus?
Sorry?
Plus?
Yes. Yes, you're right. So you see that this is the positive trefoil, right-handed trefoil. And for left-handed trefoil, it will be correspondingly T minus 1 plus T minus 3 minus T minus 4. And so Jones distinguished easily right-handed and left-handed trefoil, which was not so simple before. And because of this stuff, so because of this formula, they are different. Jones got Fields Medal in 1990. Other questions? Remarks, please. So if no questions, thank you very much for your attention, for following my stupid things. Thanks.
No. Thank you very much. It's very interesting.
Goodbye.
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 Is it last lecture?
Yes.
Oh.